Welcome to checking for convergence, this time using the limit comparison test. So the general idea here is if we want to know if an improper integral converges, so if we want to know if an integral from a to infinity of f of x dx converges, with f continuous, it actually works to find another function, g of x, which behaves in the same manner as f of x. So we can find another function, g of x, with similar end behavior. To f. So if, for example, if f ends up looking like x, then we would want to find a g that ends up looking like x. And then we can determine convergence of g instead. Or convergence for g instead. So more formally, what exactly are we looking at here in terms of similar end behavior? If f and g are both continuous, on the interval from a to infinity, where a is included, and if the limit as x goes to infinity of f of x over g of x is equal to L. In other words, it exists and is finite. Then what this means is g essentially acts as a scalar multiple of f. And we wind up getting then either first option is both the improper integral from a to infinity of f of x dx and the improper integral from a to infinity of g of x dx. Either both of these converge, or both of the improper integrals, so both the improper integral from a to infinity of f of x dx and the improper integral from a to infinity of g of x dx diverge. So if we can find a function that behaves essentially in the same manner at the end, up to a scalar multiple, then the improper integral either converges just like the other or they both diverge. So let's go ahead and look at an example. So in this example, let's determine whether the following integral converges or diverges. So here we are looking at the improper integral from 10 to infinity of 1 over the square root of x to the 6th minus 4x plus 2. So just a quick note. Note for x greater than or equal to 10, x to the 6th minus 4x plus 2 will definitely be greater than 0. And so we have that our function 1 over the square root x to the 6th minus 4x plus 2 is continuous on 10 to infinity. Furthermore, note again that 1 over the square root x to the 6th minus 4x plus 2 will behave similarly to 1 over the square root x to the 6th for large x. And so 1 over the square root of x to the 6th is essentially 1 over x cubed. So what we can do then for large x, so what we can do then is we can check that this limit is finite, and then we can base our convergence off of that. So going to check the limit. We're going to take this 1 over x cubed as our g of x. And so essentially we're going to look at, if we take the original function as our f of x, this 1 over x cubed as our g of x, then we will have, we're looking at the limit as x approaches infinity of 1 over square root of x to the 6th minus 4x plus 2 all over 1 over x cubed. This is the same thing as just the limit as x goes to infinity of x cubed over the square root of x to the 6th minus 4x plus 2. And if we wish to evaluate that limit, we are going to an infinity over infinity case. So we can go ahead and apply L'Hopital's rule or apply any other trick we wish. One trick we can apply is to just multiply by a 1 over x cubed up top and down below. So if we just multiply by a 1 over x cubed up top and down below, we are looking at the limit as x approaches infinity of 1 up top. And then if we toss that x cubed inside the square root, it becomes x to the 6th. So we would have x to the 6th minus 4x plus 2 all over x to the 6th inside our square root. This becomes the limit as x goes to infinity of 1 over the square root of 1 minus 4 over x to the 5th plus 2 over x to the 6th. And of course, as x goes to infinity, this winds up just going to 1. So in this case, the limit exists and is finite. We know that the definite integral from 10 to infinity of 1 over x cubed dx converges. And so therefore, we have that the definite integral from 10 to infinity of 1 over the square root of x to the 6th minus 4x plus 2 dx must also converge. For one more example, let's go ahead and determine whether the following integral converges or diverges. We are looking at the improper integral from 1 to infinity of 1 over the square root of x plus 1 over x dx. So again, note x plus 1 over x is greater than 0 for x greater than or equal to 1. And so we have that 1 over the square root of x plus 1 over x is continuous on the interval from 1 to infinity. Furthermore, note that square root x plus 1 over x will behave like square root of x for large x. And so that should mean that 1 over the square root of x plus 1 over x should behave like one over the square root of x for large x. So we will go ahead and take our 1 over square root x plus 1 over x as our f of x. 1 over square root x will be our g of x. If we look at our limit, we have the limit as x approaches infinity of f of x over g of x. As the limit as x approaches infinity of 1 over the square root of x plus 1 over x divided by 1 over the square root of x. This is equivalent to taking the limit as x approaches infinity of the square root of x over the square root of x plus 1 over x. We can apply L'Hopital's rule, or we can just play the same trick we played last time. If we just multiply by a 1 over square root x and a 1 over square root x, then up top, we are just looking at the limit as x goes to infinity of 1 over, throwing that x and square root x inside the square root, we would just get a square root x or an x over x. So we'd have an x plus 1 over x all divided by x inside our square root. This is just the limit as x goes to infinity of 1 over the square root of 1 plus 1 over x squared, which again is simply equal to 1. So this limit, once again, exists. We know that the improper integral from 1 to infinity of 1 over the square root x dx, otherwise known as the improper integral from 1 to infinity of 1 over x to the 1/2 dx. We know that this integral diverges. That therefore tells us that the improper integral from 1 to infinity of 1 over the square root of x plus 1 over x dx also diverges. So both the direct comparison test and the limit test can be useful. Let me update my screen quickly. Again, both the direct comparison test and the limit comparison test can be useful. It's just largely a matter of personal preference, which one you want to use. Limit comparison can be a little easier just because you don't have to show that the two functions are always f is trapped below g or f trapped above g. But these are two methods you have available to you for checking if improper integrals converge or diverge. Right, that is the end of chapter 6, all on integration techniques and improper integrals. In the next chapter, we will move on to applications of integration.